Hello everyone and welcome to this video tool on VPN verification of poisoning in neural networks. Model poisoning is an important type of security challenges for deep learning. In VPN, we formally verify if a deep learning model has been poisoned or not. I'm Yu Cheng from the University of Manchester, and this work is done together with Usman from University of Texas at Austin and Divya and Corina from NASA AMIS. Let us start from one example. Let's say there is one neural network for robot recognition, and it successfully recognizes Rob, KVRC, Xboot 4000, and 1145G. However, by placing a simple patch at the bottom corner of each image, all of them suddenly were wrongly labeled as the Hollywood movie actor A.J. Buckley. This is one typical behavior caused by model poisoning. When a model has been poisoned, it still performs well on normal data, making the correct inference with the normal inputs. At the same time, when the input contained some trigger configured by the adversary, the poisoned model will result in a particular output called the target label. That is, the attacker creates a backdoor in the model. In our previous robot recognition neural network backdoor, the trigger is the colored patch placed on the bottom of each image, and the target label is A.J. Buckley. Model poisoning can be a result of data poisoning, in which the attacker contaminates the training data of a deep neural network in order to get a desired outcome at inference time. A backdoor can be also imported into an already trained neural network. To tackle the model poisoning challenge, we propose a formal verification-based solution. We first formulate the model poisoning problem as a safety property that can be checked with off-the-shelf verification tools. We then develop an algorithm to formally verify that a model is free of poisoning. Alternatively, it finds a backdoor trigger if the model is indeed poisoned. The poisoning-free proof part of this work distinguishes it from existing work on backdoor detection. To make things even more interesting and useful, we leverage the adversarial transferability in deep learning for applying our verification results to large-scale convolutional neural network models. We believe this points out a new direction for improving the scalability of neural network verification in general. Our work is very generous for the attacker. The attacker is allowed to access the training data of the model so that backdoor triggers could be planted into the input images of the neural net. We do have an assumption on the shape of the backdoor trigger, and it must be in a bounded region of the input images. For example, for these digits images on the slide, the backdoor trigger is the white color square on the bottom. And for those traffic signs, there is a Firefox logo on top. That is the backdoor trigger. The bounded shape assumption is still very practical and realistic. There could be more complex backdoor triggers that require extension of our current work. Here we give the formal definition for model poisoning. There is a deep neural network that is a function f taking input x and returning y. There is a finite set of test inputs t that are correctly classified by the neural network, and the target label is y-target. A neural network is said to be successfully poisoned if there is a poisoning operator such that for any input from the test set T, after the poisoning operation, it is classified by the neural network as the target label. In reality, it is not necessary to have all inputs in the set T to be successfully poisoned. The poisoning could be regarded as successful as long as there is a high enough portion of inputs in T are misclassified as the target via the poisoning operation. This is what the tolerance of poisoning misses K is for. Say that I have a self-driving car that contains a deep learning component for recognizing traffic signs. Is there a poisoning operation that by placing some backdoor trigger on the traffic sign images, the self-driving car simply turn right? That is the poisoning target. Once we have this question to solve based on the model poisoning property to verify, the first thing we did was to take a look if existing neural network verification tools could solve our constraints. This is a list of such tools from VN Competition 2021. I installed all of them in my computer, and I saw several difficulties to directly use them for solving our model poisoning constraints. Typically, these tools are good at verifying local robustness properties or other properties of one single input. However, the model poisoning property formulation is based on a set T of inputs. So what could we do? We really want to explore to what extent existing verification tools can be used to verify this newly defined model poisoning property. This motivated us to develop the following VPN algorithm. Now let us go into details how VPN works. Given a set of input images, VPN enumerates each of them to see if it could identify a backdoor trigger. We do not know where exactly the backdoor trigger could be placed on top of an image. It could be anywhere. Therefore, VPN considers all possible places where a trigger could be. This is not too bad. For low-dimensional input images, there are a few such bounding boxes to check. For high-resolution images, this number is in thousands. Now, for a particular potential backdoor position on top of a particular input image, that is, stop traffic sign in our case, are there pixel values such that by replacing the original pixels with these new pixel values, our stop traffic sign is then misclassified by the neural network as some target label. We give this task to the solver if the constraints are set, and we obtain the pixel values within that bounding box that would make the stop traffic sign to be misclassified by the neural network as the target. Will this result also hold for the rest of images in the test set? We could check it. If this patch we just found indeed result in all images to be misclassified by the neural network as the target, we confirm that this neural network model has been poisoned and the evidence is here. That is the backdoor trigger. Otherwise, although this patch leads the stop traffic sign to be misclassified, it could not be generalized to other images in the test site. We then call the solver again to return us some different pixel values within this bounding box. It could happen that all possible values, pixel values within this bounding box do not support a valid backdoor trigger. Then the solver will return unset and the VPN algorithm goes to the next bounding box on our traffic sign. It could also happen that all possible bounding boxes on this image cannot result in valid backdoor triggers. At this time, VPN either goes to check the next input image on the test site, or if a sufficient number of images have been checked, then congrats, the model is poisoning free. This is how VPN works. Its design takes into account the compatibility and availability of existing neural network verification tools. The solver in VPN could be any of the neural network verification tool we just saw, as long as it generates counterexamples. In this sense, VPN enables existing neural network verification tools to solve this new problem of model poisoning. Not only so, VPN also innovatively boosts the scalability of neural network verification. Neural networks learn from the data it is trained from, and models with the same training data share similarities, including similar vulnerabilities. If we consider model poisoning in real world, it is quite easy to poison a complex model that goes beyond the scalability of any existing verification tools. What can we do then? Shall we simply ignore large-scale neural nets and pretend they do not exist? Of course not. Here is our proposal. Besides the large complex neural network model, let us, using the same training data, train a smaller, simpler model that can be handled by VPN verification. If VPN identifies a backdoor in the simpler model, will it be transferable to the larger neural network model? Or else, if VPN proves that the simpler model is poisoning free, what can we say about the more complex one? In the next, I'm going to show you some of our results on this. We trained 6 neural network models, 4 models for MNIST digit recognition and 2 models for GTSRB, that is German traffic sign recognition benchmark. Among 4 models for MNIST, 2 are simple fully connected neural networks with 100 and 200 neurons respectively. And the other 2 are convolutional neural networks. One has more number of parameters than the other. GTSRB is more complex than MNIST, and fully connected neural networks will not for it. So we trained 2 convolutional neural networks. One is more complex than another. All these models were poisoned. The white square at the bottom is the backdoor trigger for MNIST, and the Firefox logo is the trigger for GTSRB, as we also saw in the previous slide. We tested 2 verification tools in our VPN framework, and they are Marble and NNEUM. More details of the models are also available in our GitHub repository. We apply VPN on the simpler models, the 2 fully connected neural networks for MNIST and the less complex convolutional model for GTSRB. What would the results look like? Let us start from MNIST. Here are 3 examples of the backdoor triggers found by VPN on the first fully connected neural network for MNIST that has that one has 100 neurons. The trigger is the bounded shape at the bottom, and the black color background is only there for visualization purpose. And this one is for the fully connected neural network 2 for MNIST. Very interesting. How effective would these triggers synthesized via VPN? So we place each trigger we just have here on top of the original test data of MNIST and check how the two neural networks would perform. The number in this table is the attack successful rate after placing the trigger on top of clean input images. A, B, C are the three triggers found from MNIST fully connected neural network 1, and D is from MNIST fully connected neural network 2. Interestingly, the trigger found on MNIST FC1 can also result in high poisoning successful rates on MNIST FC2 and vice versa. Even more interestingly, if we place these synthesized triggers on inputs for the two convolutional neural networks, they still work, although the attack success rates are not as high as their values on the simple fully connected neural networks. This observation is very encouraging. It points out a new direction. When the model is too big, too complex to be handled by verification tools, don't worry. If you apply your verification on some simpler, smaller networks, the outcome is transferable to the original model. Similar results hold for GTSRB. VPN synthesizes a more colorful backdoor trigger for GTSRB convolutional neural network 1, which is the simpler one for GTSRB. Then, by using this trigger, the model poisoning achieves significant attack success rates on both GTSRB models. It is worth noting that the attack success rate is even higher in the more complex GTSRB convolutional model. This could be caused by the fact that VPN does not optimize the trigger values it finds, as long as there is a sufficient number of test inputs being successfully poisoned. However, this requires further investigations. NNEUM is used for GTSRB as the verification tool, and it took the tool more than 1 hour to solve the backdoor trigger values. This gives you an intuition how meaningful the transferability in VPN could be if you think about verifying directly applying the tool to verify the even more complex GTSRB neural network tool. So far, we have applied the VPN to poisoned models, and it successfully identified the backdoor in these models. How about non-poisoned models? To better understand this, we trained 4 clean models for MNIST that have the same architectures as their poisoned counterparts, as we just saw. By clean, we mean during the training phase, we do not purposely embed backdoor into the model. We then run VPN on the first clean, fully connected model with 100 neurons. Even we do not purposely poison the model, as we see here, there still exists backdoor trigger that leads the neural network to misclassify the inputs as some label 2 with 57% of attack success rates. And this attack is also transferable to the other fully connected neural network model 2 for MNIST. However, this time, this trigger has no effect on the two convolutional neural networks. 2 points to elaborate here. Even when there is no purposely poisoning, there can exist backdoor, that is, the vulnerability in a model. We can also see that the attack success rates using the trigger synthesized on clean models are not as high as their counterparts from purposely poisoned models. This could be useful for distinguishing clean model and purposely poisoned model. Secondly, for clean models, the synthesized trigger from fully connected neural network is not transferable to the convolutional neural network. This is not really a surprise, as the training dataset is clean. The cause of the poisoning behavior is more likely to be caused by the internal parameters of the model, and the convolutional model have much more complex internals than the fully connected one. Some final takeaway. We now have VPN, which encodes model poisoning property, and you can plug your verification tools into it for formally verifying poisoning in neural networks. Furthermore, the transferability in machine learning helps us make your neural network verification more scalable. We hope that VPN is a starting point for more formal verification research on security properties in machine learning. There are lots of possible follow-ups. There are more complex poisoning triggers waiting for us to solve. We demonstrated that a poisoning trigger VPN finds on simpler model can be transferable to more complex, larger models. What if the VPN technique proves that a simpler model is poisoning free? What can we say about the more complex model? There is some useful related literature on this, but more reasoning is still needed in this direction. Clean models also have backdoor. Can we use this information to make the training set even cleaner for retraining more secure model? I wish there are other thoughts in your mind too. Last but not least, you can download these models we just saw and try it using your favorite neural network verification tools. Thank you.